We have a particularly fun, oh, Jack's here. Say hello to Jack, people. Wait, there he goes. Hey, Jack. What's up, Jack? We have a particularly interesting science biography today when we get to it towards the end.
Hi, Jack.
Those are always fun. Hi, Jack. All right, let me get the slideshow. Oh, yeah. Okay. Let's get this. Oops. Let's do that. Oh, he's chatting. What's he saying? He said hi.
Hi.
So before we start, I want to tell everybody that this is like a really sketchy connection today because Jason's changing out all the equipment kind of one thing at a time, and like we didn't have internet for half the day yesterday and it kind of got weird. So things will load like they're bumpy, for lack of a better word. So you're going to see some bumpiness and just please forgive it because that's the best we can do. So we are talking today about matter and change, and a lot of this stuff is going to be reviewed for you guys. Some of you guys, it's probably not reviewed, it's probably newer, but we will see how we do. So matter and change. All right. I'm gonna take everything a second to load, like I said. So what's matter? Who can tell me what is matter? Okay, Mother.
Everything that has. Yeah. No. Wait.
Weight's close. What's the rest of it? Mass and. All right, Drew.
Takes up space.
Takes up space. All right, there. I thought Drew's trying to be like 4 inches taller. Stretching. Everything that has mass, anything that has mass takes up space is matter. What's the difference between weight and mass? Alex. Noodle. Can't even swallow fast enough. Good gracious. Do you want a seat? Do you need a seat, Parker? Like a chair? We have other chairs there, right? If you want to, there's the folding chairs are in the pub room. If you want to grab one, you sure? All right, cool. Say it again.
Weight changes based upon the gravity,
Right.
whereas mass is constant.
Right. So weight is gravity's effect on mass. Mass is constant. So for example, if you take astronaut Bob, and astronaut Bob here on Earth, and he weighs 200 pounds, he's a big dude. And then you send him to space, he's no longer going to weigh 200 pounds, but all of him is still there. We didn't lose part of astronaut Bob, right?
One might have.
Well, you know, hopefully not. So did anybody watch the Artemis launch get scrubbed? Yeah, me too. So Friday is a great day to watch. You can tune in. I really like the Everyday Astronaut. I think it's Everyday Astronaut. I shared the link and I'll share it again. But he's a guy who just had like his own YouTube channel, and then it just went huge, and now NASA like totally backs him up. It's pretty awesome. So anyway, does anybody know what this program's about? The Artemis program? What is it?
Building a moon base eventually.
It's building a moon base. So these rockets these first ones are going to go like up and around the moon, land on the moon, that kind of thing before they take people up. But it's really cool. So if you've watched any of the launches over the past year or so that they've been doing with the rockets that they've been landing, that's why they're doing it. It's for this program. So it's gonna be really cool because you guys are gonna see people walk on the moon in your lifetime. And for me too, I've never seen that. That happened before I was born. So I've never seen anybody walk on the moon, and I'm gonna get to see it. And there will be a base up there, which is really kind of wild. So matter, let's talk about matter. So we said anything that has mass and takes up space. So who wants to define an element for me? Who can do that? All right, Piper.
A substance that can be broken down into atoms.
That's right. A substance that you can only break down into,
Substance.
right, atoms or simpler substances. Like, ooh, some of these are disappearing together. Okay. Yeah, so your element is basically, it's your simplest form of any substance where you can't break it down any further unless you're going to break it down into subatomic particles, which is a whole nother game. So you have an atom, and the center of your atom is your nucleus, right? That's the very center. We use that word for lots of things. The same thing for cells when we did biology last year. So what is in the nucleus that contributes to the mass but doesn't have a charge? Bailey? Neutrons. All right. And how about what doesn't contribute to the mass that does have a charge? Chloe?
Electrons.
Not in the, do the other way, in the nucleus.
Oh.
She's swallowing too. I love it. You're fine. Protons. All right, good. All right. So then protons, and then she said electrons, and those are the ones that are going to go around the outside of the nucleus, and they have a negative charge. Can anybody try and describe what an atom looks like? James, you want to give it a shot? Like, how would you describe an atom? Y'all are all trying to.
What atom? Like a little vibrating ball.
Yeah. So we try to draw atoms, right? We try to draw them, and it's really difficult because, we see models, which helps us conceptualize. We talked about how models are good, but you've got, this nucleus in the middle and everything's moving and vibrating. And then you have these electrons. And sometimes you see models where it looks almost like a solar system where they're just going around in circles, but they don't really do that. It's more like a cloud, like a buzz around the outside of it. So so the periodic table is where we represent our elements. And if you do chemistry with me, I have a big one. It's like really big. I roll it out. It's huge. And you can really see everything on it, which is cool. So we put our elements on the periodic table and they have, I know it's unstable. Don't tell me this. What am I supposed to do? Nothing. Thank you. So what is the atomic number representing? Okay, I'll do Piper.
The amount of proton in the atom's nucleus.
Okay, so the amount of protons, where did I put Piper? Made everybody a little circle, but I haven't memorized where everybody is yet on here. Yes, so the number of protons, that's gonna be your atomic number.
It's saying display unstable.
Yeah, it's gonna do this kind of stuff, and I just thank you, Dominic. It's just gonna do it till Jason gets it all set up. He was up till like 2 a.m. on Monday night because we had no internet. Monday morning, it was fun. And it's just routers. We had a router die. And anyway, you see the little white towers? We have them all over the house. They're extenders for the Wi-Fi. Anyway, okay, so what's the mass number represent? Milo.
The combined number of protons and neutrons.
Right. Combined number of protons and neutrons. And when you're talking about like the mass number, it really has more to do with the mass of the neutrons, right? Because the protons really don't have a whole ton of mass. They don't contribute too much. Go on. All right, so we talk about electrons having energy shells. Who's seen this before, this concept before? Yeah, okay. So I know if you had chemistry with me, you've seen this concept before too. So right there, it kind of shows you like there's a center and then there's all these concentric circles with different numbers. And those numbers represent the number of electrons that can be held in that shell, but they're not circles. They're like, you ever had an everlasting gobstopper, like the real kind, and you start sucking on it and it's red and then you take it out of your mouth and it's green and then you take it out of your mouth and it's blue, kind of like that, layers upon layers. Yeah.
So I don't know if this is a funny point, but is it supposed to be this, is there supposed to be an 8 between the second 18 and 2?
Might be. Shoot, I can't remember at the moment. I'll double check. I think what you're thinking, so there's like S and then there's like an S1 and then there's like a P, P1, P2. That may be a sum or something, but I'll check it out. So yeah, so basically what you care about when it comes to how one element interacts with another element is the valence electrons. And those are the ones that are on the very outside because those are the ones that are accessible to interact with others, right? The ones that are down in the middle, they don't really interact with others because they're way down, you can't get to them. It's the ones on the outside. And there's math involved where, this guy can take 2 more before his shell is full, and this guy has 2 extra in the next shell. Woo, they'll be friends and they'll join together. So that's how you end up with bonds and stuff. Now, chemical reactions are when you break bonds or make bonds. We'll talk about those in a minute. So you have isotopes and ions. So this is something that'll come up when we do our science, especially the isotope stuff, because we do dating with isotopes. So an isotope has a different number of neutrons, right? And radioactive ones, which are the ones we use for dating and stuff, they are unstable, and over time they emit a little bit of radiation, and we can test that amount of radiation to tell exactly how old something is. And so it's a whole big bunch of chemistry stuff, and you get into like half-life and all this business. But for right now, be aware that you have isotopes and they have a different mass number because they have a different number of neutrons. And then you have ions and they have a different number of electrons. What's special about an ion when it comes to interacting? What you get?
They form ionic bonds and form salts.
Yeah, they form ionic bonds. A lot of that is salts. Very good. Yeah. So like today you had some salts going, but like if you get a table salt, which we'll talk about, like sodium chloride, that's your table salt. That's because you have an ionic bond. You've got basically one of the atoms is kind of stealing an electron from the other one, as opposed to sharing, which we'll talk about too. So the thing about ions is they have a charge. They're either positively or negatively charged. And this is how batteries and whatnot work, all of that. All of this electricity comes down to that. So here's some guesses. Let's see if anybody knows, or maybe it's in your book. So what are the most abundant elements in the universe? Okay, Alex, what do you think?
Hydrogen and helium.
All right, now why is that?
Because that's what most stars are going to be made out of.
Yeah, and how about our sun? What happens in the core of our sun? With hydrogen and helium. Do you know,
Fusion.
Bailey?
They combine
Yeah,
and then the energy, what goes back.
right. So yeah, fusion. What you got, Drew?
I was gonna say, we grab and pull some together.
So basically, what's going on in the sun is you've got hydrogens coming together, making heliums, and vice versa, and all of that is what's producing so much heat and light. That's the chemical reaction that's occurring there. So that's why you have so much hydrogen and helium. And yeah, as Alex said, stars are made of hydrogen and helium. So how about Earth's crust? What are our most abundant on Earth's crust? Drew.
Isn't it oxygen, nitrogen, and nitrogen?
Maybe you got some of them right. What you think?
Nitrogen, carbon, silicon.
Oh,
Nitrogen, carbon, silicon. Anybody else have a guess? What?
nitrogen, carbon, oxygen.
Oxygen, carbon, and oxygen. All right, so what they are is oxygen, silicon, and aluminum. Not what you expected, right? Where do you see aluminum? What do you use it for?
Making various things out of metal.
Yeah, what's an example of something?
Aluminum baseball bat.
What were you gonna say? Milo, were you gonna? No. Liam, were you gonna say something?
I would say like tinfoil.
Yeah, well, aluminum foil, but yeah, not tin, that wouldn't work. Yeah, great. And you've probably seen like the tractor trailer trucks that have the aluminum, like they're hauling those small aluminum containers, soda cans. Aluminum's very malleable and it's also very abundant, as we see. Why don't we, copper's also very malleable. Why don't we make our foil out of copper? What? It's conductive. Why else?
There's not as much of it.
Yeah, there's nowhere near as much copper in this world and this planet as there is aluminum. So aluminum's cheap. There's tons of it. So it's easy to just make aluminum foil and it can cost next to nothing. But copper is so expensive that people will find abandoned houses, go in and rip all the electrical wires out so they can strip them and sell the copper. No joke. That's a lot of work.
People steal copper and sell it for money.
Yep. Yeah, they do. Pennies are not made of solid copper anymore, right? They have a core that's like nickel.
It's zinc.
Yep, zinc. That's right. Zinc. There you go. Yep. So let's talk about combining. So how do we make molecules and compounds? So your examples you got here are compounds that are composed of two or more elements that are chemically combined. So your first example there is sodium chloride. That's your NaCl. See that? So that's going to be an ionic bond, which we talked about a bit ago, because it's a salt. That's your table salt. And then the FeO, that's iron 2 oxide. What's that look like? Anybody know what that is?
Rust.
Rust. Right? Okay, that's rust. So
Iron rust.
iron rust, right? So if you see one of those old cars sitting out in the field and it's all rusty, that's because the iron came in contact with what over time? Through oxygen over time. There you go.
Oftentimes in the form of water.
Yes, very often because it's nice and wet. Gross, totally true. Okay, so molecules are the smallest unit of a compound. And we tend to talk about molecules as being covalent bonds, sort of a science conversational thing. But really, if you get any of these compounds, the smallest unit is a molecule. So this first one in the example is glucose, right? And then the next one is water. Can anybody tell me anything about the bonds in water? What kind of bonds they are? Does anybody know, Alex? Do you know?
Polar covalent.
They are polar, and yeah, and what else? They're hydrogen, right? Okay, so hydrogen, and it's a polar molecule. Okay, so what does it mean to be a polar molecule? James? The molecule has, yeah, and what kind of charge on either side? Positive on one and then right, opposite charge on either side. So that's important because that is why water conducts electricity. It's also why water can do what it does. It's the hydrogen bonds allow for water to stick together. That's why you have, you know, surface tension on water. And oh yeah, it's lunchtime for the dove couples. Here they are. These are the doves are the only ones that do what this guy's doing. You see him sliding? They do it for fun, I swear. They stand on the thing and they slide down and they flap their wings and do it again and again repeatedly. So it must be for fun because clearly they're not eating nutty things. All right, so chemical bonds. So here are our types of chemical bonds, our basic types. So what is the first one here? Attraction of two atoms for a shared pair of electrons. Bailey? Oh, come on, you got it. Shared, you know this anyway, you know it, shared electrons. Give up, pass it to, oh, Chloe.
Covalent.
Covalent, very good. Good job, Chloe. So covalent bonds are when you have two atoms that are attracted by a shared pair of electrons. Okay, when you've got one atom transferring electron to another, dude, those are ionic. Very good. That's what we were just talking about with the salt and whatnot. That's an ionic bond. All right, so when you have a bond that is shared like covalent, but the electrons repel each other, this is what we were just talking about a little bit ago. Piper.
Polar?
There you go. All right, she's got it. Polar. We got that. All right, and then where did I put you on here? I swear I can't find you. There you are. That's hydrogen, obviously, and I didn't mean to tap the last one. Last one's metallic. Okay, so hydrogen bonds we talked about because they have hydrogen on top. And then your metallic bonds, these are where you've got positive ions holding together negative electrons, and this is what allows for conductivity. Metals are conductive. They're also malleable. You can change their shape, right? You can hammer, forge stuff. You know, you've seen those guys. You ever watch the Forged in Flame or whatever, Forged in Fire? The guys make the knives, because, and that's all has to do with the way they're bonded. Yes.
Metallic bonds are like a giant soup.
Yeah. Kind of like a really, well, they're not brittle. Metal isn't brittle, and it has to do with the way the bonds are shaped.
Sturdy soup.
Like a Play-Doh. Like a, yeah, there you go. Sturdy soup. Now, ions, we have two different types of ions. Positive ions are called what? Do we know?
Cat ion.
Cat ions. How do you know that? How do you remember it?
They're positive.
Yeah, they're positive because they are positively adorable, or the cutest ion ever. They're positive. So you remembered your cat ion. Good. And what's the other one? Wait, do it again, Bailey.
An ion.
And how do you remember that?
Good.
It's an onion. It's an onion with a negative attitude. That's how you remember cation and anion. It'll stick with you forever if you do this. I wish somebody had done this with me because I have the hardest time with them. And then I found this like 20 years later and went, stuff. So why didn't I have that? So yeah, there you go. Anions are the little angry onion, you know, and then you got the positively the cutest ion ever. Woo! That's fun. Hello. Doing that left-handed, that's not easy. All right, so moving on from that. So when you get the change of one or more substance into other substances is when you have chemical reactions. Now, thank you for telling me, there are 7 signs of chemical reactions here.
Jax put something in the chat.
Yeah, I know. It'll go away in a minute. There it goes. All right, somebody give me one. Hang on. Let me get my 7 points out here. Okay, 4, 5, 6, 7. All right, James, what's one? Heater or temperature, and a temperature change, right? All right, let me get into that. Bailey.
Gases or bubbles.
Gas is released. Okay, Piper.
I don't know if this counts, but a color change.
That counts.
Yep.
Alex?
Precipitation formation.
A precipitate. That's the hard one. Yeah, he gets the hard one for you. There you go. Your
That's the hard
precipitate.
one?
Yeah, because people don't think of that one. Your precipitate is when you have a solution and then something in it kind of solidifies, comes together, and falls out. Like precipitation is anything falling out of the sky, right? Can be snow, can be rain. So that's a precipitate. What you got?
Crystallization.
That's a precipitate. Who has another one? What do we forget? How do you know? Oh, this is the worst one. Okay, what have you got? You got one?
No.
Smell, I was gonna say. How do you know, my example was gonna be, how do you know if there's a dead baby bird nearby? Because they are the worst. You know what I mean?
How is that the example you came up with?
Because you know if there's a dead baby bird nearby without seeing it.
But why is that what you?
Because that's the first thing I think of is like a really strong smell because it's one of my least favorite smells.
I can say, how do you know when your soup is starting to cook or something?
No, it could be like, how do you know when your apples are rotten? But I'm telling you, dead baby bird is a very specific smell. You smell it and you're like, there's a dead baby bird around here. Am I the only one that smells dead? Like, you go out in the woods and you know, it is very distinctive. All right, so we got two more. What are we missing? Alex, what you got?
Light,
Light, production of light. What's an example of that? Could be. Mhm. Think about Halloween.
glow sticks.
Glow sticks. All right, I got one more. What are we forgetting? Let's see. Oh,
Heat. color?
we got that one. Temperature change. All right, so we have production of odor. Got that. Formation of precipitate.
Sound.
That's the one. Evolution of gas, change in temperature, production of light, production of sound.
Who gets electrical energy?
Actually, nobody did that one. I have an extra here. I don't know why. but I do.
It's been swapped out for something else.
Yeah, I don't know what. That's weird. What did we say? Precipitate? Temperature? No, maybe I gave somebody, maybe I put one or counted wrong. I probably counted them wrong. So yeah, sound and then absorption or release of electrical energy. There we go. All right, so moving on from that. So the change of one or more substances into other substances, we're still talking about chemical reactions. So what do you call, okay, how about this? If I don't even have to give an example. My lunch here is this pasta salad. What kind of a substance is this? Go ahead, Liam. You know? You thought about it.
I was just.
Solid.
It's a bunch of solids together. Can I separate it?
Yes.
If I wanted to pour it out on the table, it'd be really gross. Could I pick the tomatoes out from the pasta?
Yeah.
What is it?
Homozygous mixture.
No, you're close.
Solid solution.
You're close. It's a mixture, right?
Oh.
You're making it too hard. So it's made up of two or more different chemical substances. They're not chemically bonded to each other. Each substance retaining its own chemicals. Yeah,
Next one, solution.
very good. All right, so give me an example of a solution. Somebody who hasn't gone as much. Chloe, you can do it. Can you think of a solution?
Hot chocolate.
Perfect. Great example. You can't take the components of that apart, can you? And even if you could get the cocoa out, that dissolved sugar is going to be really hard to get out of there. We have two things in a solution. What are they, Liam?
Solvent and solute.
Right, which is which?
Solvent does the dissolving,
Mm-hmm.
solute is dissolved.
Right, so the solvent does the dissolving and solute is what's dissolved. In your lab, your solvent, or your solution was in your test tubes, right? And your solute was in your little bowls. And then you had, the solution was made with a solvent and a solute, and then you're just adding more solute, right? Right, cool, you got those right. Oh, they're smarty. So then let's talk a bit about acids and bases. All right, so I know my connection is unstable. I'm gonna tell you right here, because it's like 30 seconds behind, I don't know why. Yeah, all right. So what type of substance produces your positive hydrogen ions and has a pH below 7? Liam?
Like,
Yeah.
Yes.
pH below 7 is your acid. So what's the other one? Milo. It's a base, right? So it produces, what are those called? Who remembers?
Hydroxide?
Yes, yes, very good. Those are hydroxide. And that's your pH above 7. All right, now, what do you call, well, how do you describe, what's the word for a mixture that has acid in it, or just acid in general? What's the word we use to describe it? Yeah,
Acidic.
acidic. Okay, that's the easy one, right? What do you call the base one, James? Alkaline, that's it. You can say basic, but it's just so basic. That's not very helpful. Alkaline, right? Because you don't want to call your solution so basic, it's not going to behave for you. All right, so how did I eat my mixture? I'm hungry. Last week I was starving, you people left. I was like, no, fate. All right. States of matter. A lot of this is review. So what's the state of matter that keeps its shape and volume in any container? It's an easy one. Yeah. Yeah.
Gas.
Yeah.
Oh,
Shape and volume, keeps its shape and volume. Think about it. What keeps its shape? Doesn't change. Do you know it?
solid.
Yeah, there you go, solid. There you go. Had to rethink it for a minute there. Yeah. So it keeps its shape and its volume. They stay the same in any container, like a marble. I can put a marble in a glass. I can put it in a box. I can,
Put it on a box.
yeah, I can put it here or there. I can put it anywhere. It's still going to be a marble, right? And there are two types of solids that we're talking about here. We're talking about crystalline and amorphous. Now, interestingly, this can get a little counterintuitive. So your crystalline are the ones that have your geometric patterns and they make crystals. And then your amorphous ones have your particles arranged randomly, and sometimes they are referred to as glasses. Glass looks kind of crystalline to me, so in my head, that's a little confusing. But if you just call them amorphous, you won't have that problem. You have crystalline and amorphous, crystalline, amorphous, and hopefully that's not too confusing. So what is the state of matter that keeps, that shape changes to fit the container, but volume stays the same, Caitlin? That's a liquid. I don't know why I keep having European money. That's right. That won't fit in my machine. That's a liquid, right? Okay. And so you can take your liquid and you can take let's say 200 milliliters of orange juice, and you can pour it in a graduated cylinder, and you can pour it in a fish tank, and you can pour it in a glass, and its shape will change, but the volume stays pretty much the same.
Pour it in Piper's mouth.
Yeah, you could do that too. I like orange juice. Who likes orange juice? Okay, question.
Depends on the orange.
Pulp or no pulp?
No.
No pulp? Anybody like pulp? I like both, but I got people in this house who won't touch it if there's pulp in it. I think it's good. I like it when it's fresh squeezed and there's pulp in it.
I like to do it before brushing my teeth.
Yeah, well,
Wow.
that's better than doing it after.
Yes, it is better than doing it after.
My when my mother was a little girl, there was a time period where her grandparents lived in their house, just kind of like my mom lives downstairs here, same situation. And her papa, her grandfather, used to fresh squeeze orange juice for them in the morning before school and put a cherry in the bottom of a glass, and that was like his treat. It was kind of cool. What you got?
Also, don't brush your teeth and have Sour Patch Kids. It is not pleasant.
Oh, that sounds awful. That sounds
It's
really
from
awful.
Experience.
What a terrible
I have a
comment.
new recipe.
Do we want to know it? I don't know if we do, Molly.
It's the same thing that Alex said.
Don't.
That sounds really terrible, but
Especially
you
don't
know.
eat an entire bag and tear up your mouth.
to each his own, man, if that's what you like.
I'll eat like 5 bags.
My mom's best friend likes weird things, really weird things. Like she was dipping, once at lunch, she was dipping hush puppies in chocolate pudding.
Ooh.
That sounds
Oh,
good.
No,
It's sauce on it, kind of makes sense.
no, I mean, I get French fries and a Frosty.
Yeah.
That's good, but
Or like a milkshake or something.
yeah, I love French fries and the Frosty. That's actually really good, but
Yeah.
I don't know. And they were driving up to college to see me once, and she had a bagel with cream cheese, and she wrapped it in a napkin and put it in her purse. And then like 4 hours later, she took it out and ate it. My mom was like, no. She also puts popcorn in soup. Do you know what popcorn
Ooh.
does in soup? It just dissolves. She's a wonderful, wonderful, I love her, but she eats weird stuff. All right, so back to science. That is a little sciencey, like I'd like to get in her brain. So what takes the shape, what has the shape and volume that fit its container? All right, Chloe, that's your gas, right? Okay. So gas is gonna change shape. We've got gas in here. And then lastly, what's this last one here? All right, Liam, what you got?
Plasma.
This is plasma. All right, so we don't see a lot of plasma or deal with a lot of plasma. We're certainly not gonna have plasma in lab. Thank you very much. That does not sound fun to me.
There's plasma in lightning strikes.
There is plasma in lightning, yeah, and we'll talk about that when we
And
get
the
to lightning.
sun sometimes.
Yeah, we're gonna be talking about lightning when we get to it. And I have the hardest time spelling it correctly because I want to spell it like lightening, and that's a different thing. But you'll probably get a lot of brownie points there and giving you a clue. All right, so, those weren't supposed to, they all disappeared at one time, gosh darn it. Okay, so anyway, evaporation, this is your liquid to gas, right? Condensation is your gas to liquid. So let's do examples of each instead. All right. Who will give me an example of evaporation? It's easy. Go, Parker.
A very hot surface and a very hot surface
Mhm.
like pear that's been
Yeah.
on. It can evaporate water.
Yeah, the water will evaporate out. Very good. Great example. Also like a puddle outside, you come back later, that water didn't disappear, right? It just evaporated. It turned into water vapor. All right, condensation. Who's got an example of that one? Oh, come on, Milo, you got it. What's an example of condensation?
Gas turning into a liquid, like if you put, like if you would spray.
Think about, this is the easiest one. What happens if you take your, like a nice cold iced tea out on the back deck with you in Georgia? What's gonna happen to the glass? The outside of the glass. It's nice and humid and warm outside. You get all that water on the outside of your glass?
I don't think.
You don't drink
Oh, okay.
tea, whatever, ice water, lemonade, I don't care, something cold. Yeah, You get- yeah, lemonade. Yeah, so what happens to the outside of your glass? The water, and that's why is that? Why does it condense there? Do you know? What's different about your glass compared to everything else that it's around? It's colder. Yeah, you got it. Say it. You got it. It's colder, right? It's colder, and when it's colder, it causes all those little water molecules to come together because they lose energy and they stick to each other. All right, sublimation. I'm giving you my example unless somebody remembers my example. Do you remember my example of sublimation?
Dry ice?
No, that's a good example. Here's my example. Because everyone watch for it. The what?
That you said last time back.
That's one. So here's my example for sublimation, because you will see it. Okay, when it snows this winter. All right, it's gonna snow at some point. Hopefully, woo, maybe we'll get out of class, it'd be even better. Awesome. You remember this?
It's burning the snow.
Oh, yeah, okay. Burn in the snow. There is some nitwit every year. There's a different one. You can go on YouTube, they're all there. But whoever the new nitwit is gets on social media and you see this joker with the snowball. And they take a lighter and they light the snowball and it doesn't drip, but it turns black and they're like, the snow is made of chemicals, it's plastic and the government's putting it in the sky and we're all gonna die. They're just heating it to the point where the water is going from solid to gas and skipping the liquid phase and it's sublimating. And the black stuff is soot from the butane in the lighter, but they're going "Look," every year. And then it gets passed around social media. Oh my gosh, it's a conspiracy. It's not a conspiracy. Watch for them. I promise they'll show up. Why?
There's no point like.
'Cause they're ridiculous. Well, who knows? It's chemtrails. It's all the above, the same thing. All right, this is an easy one. Melting. All right, Milo.
Ice cube, putting an ice cube in your.
Yeah. How about melting with something that's not water?
Metal.
Drew. Yeah, go ahead.
Like I said, metal.
Yeah?
Or,
What's an example of like, when would you melt metal? For what?
to make anything.
To make anything. Yep.
Yep.
Yep. So if you heat up metal, that's still melting. Uh-huh.
One, I can't remember if we were missing sublimation deposition, but one of the two wasn't on the diagram.
Wow. Because they leave it out, but I put it back in here. All right. Freezing. Soy.
Like puddles or like in the winter.
Easy. What's something that's not water?
Freezer.
Yeah.
Put the blood in the freezer.
Most metals don't even matter.
Right. Most metals are frozen at room temperature. You're right, Drew. Very good. Most metals are frozen at room temperature. You have to heat them to melt them to make them do anything else. Yeah,
Like freezing juice in the freezer to make popsicles.
delicious. You heard that
Freezing
earlier.
blood.
Orange juice.
Oh, heck yes. So yummy. Anybody ever freeze Jell-O? It's
I
good.
put sparkling water in Jello before.
Oh, yeah. I haven't done that, but if you make
Really
Jell-O and you freeze it, that was really popular back in the day. You had Jell-O and then you had Jell-O pudding pops and that. Do you know who the spokesperson was for Jell-O pudding pops? It was Bill Cosby. Back in the day, did the Jell-O pudding pop commercials. It was a big old deal. It was when everybody loved him. Yeah. Before things. All right, so. Oh, skipped it. Last one. So deposition, gas to a liquid. When do you see?
Like gas to solid.
I mean, gas to solid, sorry. When do you see this? Gas to solid deposition. There's one time you see it, you may not even notice it, but How about frost on the grass? There you go. Frost on the grass deposition. All right, so next up we have law of conservation of energy. Okay, we have lots of laws. Whose law is this? Who do you think made this law? Anyone guess?
Newton?
Newton? Anybody else want to guess?
Einstein.
Einstein?
That's the-
Anybody else want to guess?
Is it the lady that you were talking about earlier this morning?
Yeah, it's actually a lot of people made this law. So this is the law that's been around for a long, long time. And it's one of those things that the more it's studied and the more scientists kind of dip their toe into that ring, it gets more and more and more refined over time. It's gotten refined over time. And there are certain people who had a real hand in refining it. This is an old penny right here. I'm gonna have to,
What years of?
I'm trying to see it. I saw it in my hand. I was like, this one feels different than the rest. I don't know, look at it later.
2000.
No. So what does the law of conservation of energy state? Who can do it? Fill in the blanks for me. All right, Piper, you do it.
Energy cannot be created nor destroyed, but rather changes shape or form.
Form. Yep. Okay. Energy cannot be created or destroyed, but rather it changes form. That's right. Okay. So if I have, let's backtrack this one. Okay. Where's something? There's something I can use as a battery in here. Okay. Yeah. If I use my remote control. No, that's not a good one. Okay. If I have a battery operated car, and it's one of those cars that you just put it down, push the button and it runs. It's got no remote. It just goes crazy. You're the ones that bounce against the walls and turn around and keep going. Woo, they make noise. They light up. We used to have those. They were really fun. So I had to put batteries in the car.
Uh-oh.
So
Your device is disconnected.
son of a gun. That's right. I can reconnect it while we're talking. So I had to put batteries in the car to make it work, right? So what kind of energy is in the batteries? All right, Drew.
Potential energy.
Be more specific. What kind though? Yes, it's chemical. It's potential energy, but it's chemical potential energy. Very good. All right. So if I have to do that, I have to put the batteries in the car. What kind of energy did the car was there with the car moving? James. Well, it's electrical, yeah, but how about, I'm talking about the actual motion of the car. What kind of energy is that? I know Alex knows. All right, Alex, what is it? It's kinetic energy if it's moving. Okay, kinetic energy is your motion. All right, now. Hold on. Stop. Guys, stop. All right, so it's trying to find my devices. It's going to be a second here because it's being weird. All right, so we have kinetic energy with the little car moving. All right, if we ran the car until eventually it ran out of battery, would it keep running?
Technically,
Once the battery is gone, what's going to happen to it if it's on a level surface? Liam.
It would just keep going until it slows down.
Okay, what slowed it down?
Friction.
Friction, very good. Friction's going to slow it down. What kind of energy does friction produce? Drew. Heat. How do you know? What can you do to show me that? There you go. You can do the Mr. Miyagi thing. All right, yeah. Y'all know Mr. Miyagi, right? Yeah. So
Raise your hand if you don't know who Mr. Miyagi is.
yeah, if you don't know who Mr. Miyagi is, you can leave now.
Die.
So Drew. Karate Kid, the sensei, you know, Mr. Miyagi. It's having a minute here. It says it doesn't want to connect. Come on.
Also learned it from Homer in science guy.
Just think. All right, so
oh, yeah, we just, we watched. I got the book. I just don't believe it.
give me a second. Let me fuss with that. Yeah, so yeah. So yeah, Mr. Miyagi did the whole thing where he clapped his hands together and he rubbed them really fast, and you can feel friction there. Here we go. Thank you. So let's go back to the car. We have friction that stops the car. Okay, the car had kinetic energy. It had friction that stopped it. The friction created heat, right? Let's back up then. The batteries had, as Drew said, potential chemical energy. All right, then how did the batteries get in the car? How'd they get there? How'd they get there, Parker? How'd the batteries get in the car? How'd the batteries get in the toy car? I put them there. Okay, very good. I put them there. So what does that mean? If I put them there, what kind of energy did I use to put them there? Yeah, it's true.
Also chemical energy in the form of
Ah, it was chemical energy and I got it from my food. What molecule are we breaking? You know,
Calories?
you're producing calories as heat, yes, but what molecules are you breaking, James? Glucose. Yes, this is why I love you guys. This is why if you eat lots of sugar, you have all kinds of bouncy energy. Alex could teach, I swear, some days. So yeah, Alex doesn't need sugar because he steals corks and all of that. So, gets a little crazy. Yeah, it gets a little wild. So, okay, let's back up some more. So I ate and I had, there's also lots of other energy involved too. Like I had to move my hand, all that, you know, there's all that energy. Whoops, up here, it's potential energy.
There was
Down.
friction.
Mhm.
there.
All right, so I ate a peach. And that's all I had all day before I put the
Yeah.
batteries in the car. So where there was energy stored in the peach, right? It was potential chemical energy, just like the battery, by the way. Same idea.
Just different form.
Yeah, just a different type of molecule, but the same concept, same form of energy, potential chemical energy. Where did the energy of the peach come from?
The either photosynthesis
Mhm.
or
Yeah.
like nutrients.
All the above, yep, photosynthesis, but, okay, so what's the source of energy for the photosynthesis? The sun, James says, pointing upwards. All right, the sun. Well, that's interesting. Okay, let's think about this then. I turn on my faucet and water comes out, right? Okay, what kind of energy is causing that water to come out of the faucet? What's doing it, do you know? It's kinetic energy. Where's it coming from? Where's that water pressure coming from? Bailey, do you know?
All the water like pushing on each other through the pipe
Mm-hmm,
creates energy to express food.
right? What's causing it to push? Do you know, Drew?
Well, it depends where you are. I'm not sure here, but it's
Mhm.
either gravitational or from a dam, like.
Right.
Not sure from.
Gravitational or from like, yeah, like turbines in the dam. Okay. Where do you see the infrastructure for gravitational work of potential kinetic energy for water pressure? Do you know, Alex?
Mountains or
Sometimes
Yeah.
infrastructure. True.
Oh, water towers.
Water towers. See water towers? You wonder what the heck they're there for? You put water up that high, lots of water up that high. You open a spigot down at the bottom, what's gonna happen? Yeah, you go. Okay, well, how did the water get in the water tower?
people put it up there, one bucket.
You
at a
moved it
time.
there. How do you suppose it got moved there, Piper?
Either by buckets or hose. Or
Yeah.
tank.
Probably not buckets. Okay, yeah. What do you think would be, what kind of machinery would you probably use to try and get water all the way to the top, James? A pump. All right. What do we generally use to power our pumps? All right. What do you use to power a pump? Think about Parker. Think about it. What do you use to power a pump? What do you think? If we're trying to pump water to the top of a tower, what kind of a pump are we going to use? You know, Chloe, do you know? What do you think? Electricity. All right, good. Now, there's a question for you here. Where is our electricity coming from? Here. Anybody know here? Bailey, do you know? Coal is, a lot of the time it's coal. Okay, we'll come back to coal in just a minute. Here, it's something else. Do you know, Drew?
Electrical dam.
Yeah, it's hydroelectric. It's right there. The dam. You drive over the dam? Who drives over the dam? Anybody? Anybody drive over the dam? You drive over the dam. There's little goats there. We talked about them last week, I think. Eating grass on the hill. So cute. I love goats. They're adorable.
They also climb and are really freaky.
And they have devil eyes, but they're really sweet. So yeah, so there's goats there on the dam. They open up the turbines. They spin, they turn, you get a generator going. Why is the water moving? Piper?
Because it wants to go forward because gravity's pushing it forward and down.
Because there's a difference in elevation, right? So it wants to go down my river, right? So this is something we're going to keep in mind next week when we do our lab, and we're going to be down the river. Now you can call and you can get, I don't trust this app. You can call the Army Corps of Engineers hotline and they'll tell you when the dam openings are. But you can go online and you can sign up for alerts on your phone. And let me tell you, I spent an hour trying to figure that out because it was the worst government website I've ever seen. I don't know if you've ever had to deal with like I don't know what it is. I don't know who designs government websites. Like Chick-fil-A should design the website and I would have been like, bing, bing, I had an app, it would tell me, it would give me like a 15-minute warning. And then I could push the button, like dismiss it, and it would say my pleasure. It would be great. But no, I had to get the damn app with the damn government, the damn thing, all the damn information. Yes.
It'd be like, the day was about to open, would you like a sandwich?
Yeah, exactly. It would be, but it's not. It's this terribly difficult to understand. It's like you have to go on a map and pick the places that interest you. So I pick the dam and then downriver for me. That should be interesting. Well, I can tell that one got in. I don't know if the other one got in. Haven't gotten any alerts yet. So I guess the water doesn't move. I don't know. So yes, the water comes out because of gravity. And that's this case. Now, if we go back to the other one, we go back to the coal. So we get coal out of the earth, right? What is coal? What is it, Liam?
Fossil fuel.
It's a fossil fuel. What's that mean? What is it exactly? Do we know? Alex?
It's made out of dead plants and or dinosaurs.
It's dinosaurs and dinosaur plants. That's right.
It's dead bodies.
Yeah. So that's what coal is made of. And it's pretty much solid carbon, right? So where did that energy come from? It's a bunch of dead ferns and it's swamp.
The energy from the dead.
Yeah, where did all those plants that now have that stored energy in coal, where did they get their energy from?
The sun.
The sun again. Oh my gosh. Do we keep coming back to the sun unless it's gravity? Yeah, and if we got really picky, we could take the gravity back to the sun. Why?
Because.
Yeah, because we orbit, right? We are kind of, it's all affected. All of that's affected by the sun and the earth. So everything keeps going back to the center of our solar system. What a shocker, right? Ta-da. It's our source of energy. Okay, now we're going to get interesting here. This is going to be the story of some long, it's supposed to play as the world turns theme, but I don't have sound today because it's all messed up. It actually played and one of the last days of our lives. What's up? Dum 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 as the world turns. And then I'm supposed to play that whole little intro, but it didn't because it stinks. So this is the story of some long dead people who thought up the concept of conservation
It's a
of
catchy
energy. This is a fun little story, So concepts behind this law, like I said, they went way back. At least the writings that we see go back to like the 1600s. Okay, so these people are really thinking about this back then. And we're going to give you today this brief bio of this one contributor who is Emily du Châtelet. I actually have an Emily du Châtelet t-shirt on order. It's supposed to be here today. It's late, so I'm mad because I was going to wear it. So she's actually, anybody want to do it? Anybody take French?
No,
No.
but I can try.
Gabrielle Emily Le Tonnelier du Breteuil Marquise du Châtelet. So she's the Marquise du Châtelet, which means she is married to a marquis, marquis. That's how they all do it, right? They all marry each other and whatever. So Emily du Châtelet is pretty darn awesome. And not just because of her science stuff, but because she was the ultimate party girl. Let's say it. So ladies, here's one of your very early women's lib people, this one, without really even being women's lib. Pretty interesting character, definitely a character. So we're talking mid 1700s. This is when she lived. And she was what we call like a natural philosopher. She was also a mathematician. She's best known because she translated Isaac Newton's most famous, best known, all encompassing work, which is, anybody want to do that? Latin? Who does Latin? Want to do it? You want to do it, Piper?
I'm interested in trying that.
Go it.
But also there's Naturals Principale Mathematica.
Yeah, close. So if you were doing church Latin, which is a little different from like traditional spoken Latin, that word principia is kind of traditional Latin, but in church Latin, it would be principia. It would have instead of a so. So it's Philosophiae Naturalis Principia Mathematica. And the T in Mathematica is what they would call a dental T. So you don't go T. It's almost like you're saying D and T at the same time. Mathematica. You touch the back of your mouth. I sing way too much Latin. So anyway, so she translated it from Latin to French, which was cool, but she also added her own comments, and that's where it gets interesting. It's actually the only French translation they use today. Same one, because it was right the first time, so why reinvent the wheel? So she included this commentary, her own notes, which added an element of understanding to these Newtonian laws of physics. that hadn't been previously understood. So her idea was that kinetic energy of motion is an element of the concept of conservation of total energy. So your energy of motion is involved in your total energy. And she's formally described the relationship between the mass and velocity of a body in motion, which Newton kind of skipped over. And the guys before her hadn't even gotten close. So this is a copy of what that looked like, by the way. And I think you can still buy that, actually. Probably still written in Latin. So they published her work in 1756, which was 7 years after she died. Isn't that the way? Isn't that the way? Do you remember from last year whose research, there was a female scientist whose research got published after she died? Remember the big one, James? Remember Bailey?
Marie Curie?
No.
Not Mary Curie.
I can't remember her, I can't remember her name, I
It was
think
like-
it's.
Photo 50.
I can remember.
54.
Watson and Crick that stole from her.
Watson and Crick stole her information, stole her
I
research.
want to say her first name was Anne, but.
Not Anne. Rosalind Franklin. Rosalind Franklin did the X-ray crystallography photo of a molecule of DNA, a strand of DNA, and not a molecule of DNA, but strand of DNA. And she was the first one to understand that it was a double helix because her photo showed that. And somebody who worked with her was a double agent, worked with Watson and Crick, took her information, took it to Watson and Crick, and they published it. And then she published hers, but hers got published like a couple days after theirs. So it looked like she copied them, which was not what happened because they copied her. And it wasn't until years later that it was corrected, that it was actually her information. And if you watch the TED Talk, I put a copy of it last year. It was a TED Talk Watson gave a few years back. He still didn't give her credit. It's like, dude, dude, really? So anyway, Emily's work was published after she passed away as well. Now, here's what's interesting about her. So she was born into these very wealthy aristocratic French families. And this is, you know, look at the date. Are we before or after French Revolution? Do you know?
Before.
We're before, right? Because French Revolution came a little after ours. Because if you pay attention to Hamilton, remember, they're like, oh, Lafayette wants our help. And they're like, we're not helping anybody else. We're too young. Remember that bit? Okay, so yeah. So, and French Revolution, you're thinking like, down with the king, let Marie Antoinette, let them eat cake, all that business, right?
Mhm.
So this is prior.
Their heads.
Up with their heads, prior to the guillotine chopping. But she would have been,
70 plus because 1776
yeah,
was.
well,
when
she didn't make it, as you'll see. But she would have been on the side of the wealthy aristocratic people because that's how she was born. So she was one of 5 brothers. She had 5 brothers, one of 6 siblings, 5 brothers. And her father, when she was little, recognized that she was like really, really brilliant. So instead of sending her to a convent, which is what they did, they homeschooled her. Yay! And they brought in all these special tutors, which never happened with girls in her time. She learned all the things that boys typically learn because her dad was like, dude, let's do this. You're super smart. So she had, I think she spoke, I want to say she spoke like 12 languages by the time she was 11 or something. I mean, very, very
At the
smart.
very least, she learned how to read Latin.
Oh, yes, she learned how to read
Right.
Latin very well. So she had lots of tutors, okay? And she received, like I said, the type of education that's typically reserved for boys, right? So she was a little different in that regard. Now, in her young adult life, she had to do what pretty much all ladies had to do, which is what? What do you have to do if you're a young lady? You have to go, what? You gotta go get married. Yep. So she was placed in a marriage, was chosen for her, despite the fact that she was like really smart and independent. And she got to marry this army officer who she found really stuffy and really boring. But this was really an arranged marriage. This wasn't like an I love you marriage. This was just like a, here, this is where we're going. Yeah, he's an army officer, so he's got a position, it's upstanding. And so they had 3 children together, but not really much of a relationship, like not close. He was gone a lot, okay? So her friends, I'm gonna put friends in quotes, were very critical of her, probably because she was so smart. And they said that, this is a quote from one of her friends, her fat arms and legs, enormous feet, and very small head with a pointed nose and shapeless mouth containing very few teeth and those decayed. Meaning what teeth she had were decayed. She was fat, she had a little head. Like, this is the way her friends talked about her. This sounds not all that different from the way people talk to people today, right? So if this has made it from the 1700s to today, imagine what social media is gonna do, y'all. I mean, for real, be nice to people, because this was unkind. So like WTF, like I said, who talks that way, right? So not only was she super smart, she was a very passionate person about absolutely everything. She's one of these people that deep dives into stuff and gets super excited. She's very hot and cold about everything she learns. So she fell in love with this dude named Voltaire. Anybody ever heard of Voltaire? Okay, Voltaire is probably the best known French author and philosopher of his time. He's still quoted today. He's a French hero. Still to this day, Voltaire is a French hero. Like, he is the dude. So she meets him because she's in a high society. She falls in love with him. And like I said, she's passionate. Now she's married. She's married. She fell in love with Voltaire, as in the Voltaire. And this is Voltaire. And this is a quote from Voltaire to tell you how he is. This is well, not a quote from Voltaire. This is taken from quotes of Voltaire. So basically, his beliefs on freedom are the reason that ultimately led to the French Revolution, the US Bill of Rights, and the decrease in power of the Catholic Church that was running France at the time, and affected Western modern society. And he says that they say that he's one of the greatest French writers and philosophers in all of history. So truthfully, this guy is a super impactful guy. He's a very important guy. And though she was married, she had no issues with PDA with Voltaire. Like, she would make out with Voltaire in the street in front of everybody, like kiss him on the mouth, totally make out with him in front of everybody. And everybody knew she was married, right? So it created a lot of drama, as you can imagine. Everybody's talking about it. Like, oh my God, what's she doing? You know, what's she doing? So she got a little tired of the drama. So did she like leave Voltaire and go back to her husband? Oh no. She actually took Voltaire to her castle. No joke. She had a castle. And she's like, come on, Voltaire, baby, let's go to the castle. So she goes to this castle and they just live together. That's the actual castle. You can go today, right? You can visit. So her family had this castle, but it was just kind of sitting there, like nobody lived in it. It was just sort of like this abandoned property that her family had. So he had money and she was starting to run low. So they renovated the entire castle. And you can think very much like HGTV, like, you know, we're going to go and we're going to like love it or leave it or whatever, love it or list it. Like, they completely renovated the castle and they put in a library, and they had over 20,000 books, which was more than most colleges in their day. So these people were like, here is the center of academia. And it did become that. Some of the world's greatest minds at the time, they would all go travel to go hang out there and talk philosophy. These people that have nothing to do but talk about stuff all day, because, you know, they were like wealthy and don't need to work. So they just talk about things all day. This is what they do. So after this, they spent 20 years together, but she had a lot of ideas and wrote a lot of papers, mathematical papers, scientific papers, and Voltaire's name had to go on them, because if they put her name on them, nobody would take him seriously. Because it's 1700s, and she's a lady, and they're like, she's not smart enough to write this. Literally, they actually, in that time period, they actually thought that scientifically, women's brains were not as smart. And not just women, other races, like everything. They had very particular beliefs about who was intelligent. And she was definitely not in that group, if you look at it from that perspective. So here she is with her, what do you call, I mean, if a guy takes a woman as a mistress, what do you call this? I don't know what you call Voltaire. Her fling? I don't know. Her on the side dude, Voltaire. And they're living in a castle with 20,000 books, and they're meeting with like all the scientific minds of their day. Meanwhile, she's still married. Everybody knows it. Nobody cares. Her husband knew it. He didn't care. For real, he didn't care. So when not studying, they were either super passionate one way or the other. These people were like, have you ever seen the couples? Like, sometimes they're characters on TV, but they're either like super in love and can't get enough of each other, or they just hate each other. That's how these two were. Off and on and off and on, and hot and cold. They fought constantly, and not just about like things couples fight about, which of course they're going to fight about. Like Voltaire dropped his underwear on the floor or something. She's going to yell at him about it. You know what I mean? It could be that, or they fought about concepts and academic thoughts. They fought about everything, off and on, hot and cold, off and on, hot and cold. Craziness, right? So Voltaire got tired of that. This is exhausting. So he decides he's going to take some long trips. He took some long business trips, and because he needed a break from her, because she was super intense, like I said. While he was gone, she fell in love with this other dude, who was the Marquis de Saint Lambert. And so she's like, oh, he's pretty cool. I like him too. So she's still technically living with Voltaire, married to another guy. And what she do? She hooks up with this dude. Yeah.
It says Army do.
Oh, yeah, you found one. Army dude, it should have said, woo, okay, yes. So this is the Marquis de Saint Lambert, and he was 10 years younger than her. So if it's scandalous enough that she's living with Voltaire, and now she's seeing this guy, the fact that she's 10 years older than him is major scandal. Like even today, we look at it, and we're like, cougar or whatever, you know, you know what I mean? But people will comment.
It's probably like 15.
Yeah, I mean, well, she was in her 40s, so
Like
still,
30.
or late 30s. Yeah, but still, it's crazy. That's not none of these things she's doing are things you quote unquote do. Okay, so
Still, you don't do it.
no, you don't. So during this time, Voltaire became super attracted. Now, this is interesting, to his newly widowed and much younger niece. Okay, so his niece, all right. Remember, this guy is a French hero. He is one of the most revered French historical figures for being a philosopher and starting the revolution and blah, blah, blah. And he falls in love with his little niece because she's now widowed. And he's like, oh, she's really beautiful. And he took her in to be his housekeeper after sending her tons of very explicit letters and waiting for her response, to which she wrote back, oh, that sounds great. Like his letters were real explicit. And she's like, oh, I'm totally into that. Let's go. So she goes and moves in with him as his quote unquote housekeeper. She's not his housekeeper either. Okay, so we're talking major scandal here. This is like a soap opera with like the smartest people in the world having a soap opera life. I mean, it's fascinating because it's crazy, right? And because incest was kind of cool in the 1700s, people were all right with it. It was totally cool for him to be with his niece. People were going to be like, yeah, you know, people were, don't worry about it. Genetically and the offspring will be totally fine. Now, also his niece was criticized for being fat. All the stuff I read talked about how she was fat and unattractive, and he was in love with her. And I'm like, good gracious, what is wrong with people? Like, this is the way they're talking about these folks. And it's made it into history books, you know, 300 years later, they're still talking about this. That's so awful. So despite these new relationships, Voltaire and Emily still had a relationship that they called platonic, which means they're just friends, which we're sure was not platonic or whatever, as I said. So Voltaire said of Emily, and I love this quote. He said a lot of good quotes about Emily, but he said she was a great man whose only fault was being a woman. So, because, you know, he had like she published under his name and all that. And that's kind of what he was getting at. So this is where Emily gets to go from being complete party girl to pretty darn heroic. So here's what she does. In 1749, she became pregnant at 42. And this is Saint Lambert's baby. So this is side dude number 2, at least extended period of time, side dude number 2. Okay, so this is her 4th child, and she is 42. Now, in 1749, you don't want to be pregnant at the age of 42 because you are an old woman. I mean, I'm 46, but in 1749, you were old at 42. Think about it. People died from diseases. People got married when they were 15, 16, right? Life was shorter, and pregnancy, even now in older women, is a little riskier. Like, do you know what they call a woman in her 40s who's pregnant? They call it a geriatric pregnancy. I'm not kidding. That's what they call it, for real. Now, one of my classmates from high school just had a baby. Like, she's 46. She just had a baby. All is well, but in 1749, it's practically a death sentence. And she knew it.
Somebody my mom knows, she's like 45.
Mhm.
She just had her baby.
Just kill me now. So yeah, I mean, I love babies. Jackie's gonna bring hers in the spring. I don't want one of my own. I'm good with that business. So she knew that it was pretty much a death sentence. Like, her chances of surviving it were not great. They really weren't. There was a chance that she would die, and it was a decent chance. So here's what she did. This is when she started translating Newton's work. She'd been doing all this talking, all these papers had been published under Voltaire's name. People are like, daggone, Voltaire is like a mathematician and a scientist and a philosopher. Because that was her stuff. So she sat down, she sequestered herself in a room. And this reminds me of J.K. Rowling finishing the last Harry Potter book, where she shut herself away in a hotel room, you know, and like really focused and wouldn't let anybody else come in and didn't go anywhere. Well, this is what Emily did. She didn't go anywhere, and she took very short structured breaks. She ate very small meals. She didn't see friends. And this is a lady who was super social, as you'll know, since she had like 2 side dudes, very social. She shut herself up in this room until she finished it.
She's still married to the first guy.
Oh, yeah, totally still married to the first guy. You don't get divorces in 1749, just take on side dudes, apparently. Now, most people are not gonna be able to get away with this, but she was like wealthy and had a castle in the middle of nowhere, so she got away with it. But I mean, people were, like we said, calling her fat and ugly and everything else, because people were not nice. And they also wouldn't accept her work. So she sat herself in this room and wrote for hours and hours and hours. And this is starting like, if I remember this correctly, she started this in like May or June, or maybe a little earlier than that. And in September, somewhere around September 1st, September 3rd, she had her baby girl. And there she was, baby girl's good, she's good. So she finished the writing somewhere around September 1st and September 3rd. Baby came on the 4th. So she finished translating Newton's book somewhere around the 1st or 3rd of September, and then she had the baby immediately. Like, let's talk about timing. She's got good timing, really good timing, right? So baby came, and Voltaire said, and he was there. He said, the little girl arrives while her mother was at her writing desk scribbling some Newtonian theories, and the newly born baby was placed temporarily on a 4 volume of geometry while her mother gathered together her papers and was put to bed. Because he's funny. So that's what he said.
I don't know if that would be a typo, but quattro has the R before the T.
You know, I copied it. So maybe it's not quattro, it's quarto. And I don't even know what that means then, huh? I'll have to look at that up. Good one, good point. Yeah, I copied that quote exactly from one of the little historical things I read. So I'm not sure.
So,
I'm gonna I'll give you a thumb for finding it. Yeah. Yeah, if I do it, it's brownie point. So, yeah, he's learned. So within 6 days of her delivery, Emily got what they call childbed fever and died. Do you know what childbed fever is today?
Infection.
Yeah, it's basically she went septic. She also had a pulmonary embolism, which was part of this. Do you know what a pulmonary embolism is?
Something to do with the heart.
Kind of, not quite. Do you know? It's when a blood clot gets in your lung. And that's not good. So she passed away 6 days after having her baby. Very sad. Yeah, very sad. And roughly a week, 10 days to a week after finishing translating Newton's work and putting her comments in. Timing again. So a friend who was there wrote about it. He said that Voltaire, who was with her at the end, was distraught in tears. He stumbled from the room and fell at the outside door. And I don't think I put this in here, but from what I read, not only did he like burst into tears and stumble out the door, but he was lying on the ground when her side dude 2 showed up. And he was there just sobbing, and this is Emily, but he was there just like sobbing in an absolute mess when side dude 2 shows up. And he actually looked at side dude 2 and said, "You killed her," basically.
he literally just showed up though.
Well, because he gets one, she's pregnant by him. So he's like, you basically, you killed her. And he also started talking to God, and he said, and I love this one. After all this, he's like, and then you give him her child. Like, I don't get her, she's gone, and he gets her child. How's that fair? It's like he was like fussing at God over it. So anyway, Emily, Emily is thankfully now recognized for the work she did, because it was pretty darn incredible. But none of that was done in her lifetime, as per usual. It's the trend until like 1970. So anyway, very cool. Party girl of all party girls, the ultimate party girl, but also really, really super bright. What do you call somebody who's very smart and very well educated in multiple diverse dimensions, you know?
Polymath?
Polymath, that's it. She was a polymath. Give me some other polymaths. Somebody tell me a polymath. James. Plato, who else? Drew. Einstein, yeah, Einstein's a polymath. He focused more on physics, but yeah, let's see who else. Bailey. Newton's a bit of a polymath, yeah. Who else? Liam?
Leonardo da Vinci.
Oh, definitely.
You
Great
see what I was
example of a
gonna say.
polymath. Dude invented telescopes, machines that fly, and painted ceilings. That's impressive. I can't do any of
He was
those
the
things.
first person to paint.
Well, no, not first, but he painted, yeah. No, he drew them out. I mean, he didn't actually produce them,
Oh, and also-
but he sketched them, like he
And
drew
he
blueprints.
documented.
It was pretty cool. Did you have another one, James? Archimedes, there's one. Good American example, Benjamin Franklin and Thomas Jefferson. Have you got one?
I'm sure it's like. She's not actually one, but Hermione Granger.
Hermione Granger's pretty good, yes. So Thomas Jefferson is a great example of a polymath, because you're talking about a guy who could think very much like Voltaire, right? And we're talking, Voltaire actually was probably thinking a lot like him. They were thinking a lot like each other. So Voltaire, Jefferson could do all that thinking, that incredible, beautiful writing. What did Jefferson write?
Declaration of Independence.
Yep. So you get Jefferson there, and then he did the absolutely beautiful writing. And then what happens? He also invents, like, he invented the those, what are they called? What are they called? The
Light bulb?
nope.
Wow.
It's a spy thing. It's got a key, like you turn it, what's it called?
Translator?
Something like that. What was it?
Kaleidoscope?
No, he invented ways to like write in code and translate it using like translator key type things, like Ralphie with the pen. You know, it's that kind of thing. He invented all kinds of stuff like that. Franklin, another great example. Great thinker, great philosopher, good writer, messes with electricity for fun.
Sure.
Does anybody remember the guy, just as I said electricity, I'm just wondering if you remember, who's the guy that hung the frog legs on the fence? Do you remember that scientist?
Yes, but no.
Yes, but no.
Yes, but not the name. He was French. I
No,
think.
he was Italian.
I'm not good with names.
Galvani. Remember Galvani hooked the frog legs to the fence during an electrical storm and watched the legs move during the electrical storm? So, yeah. I like to throw in biographies when I can of scientists, because I think it puts things into perspective and it's interesting. It sort of humanizes the lesson. Like, there were people, these aren't just concepts and thoughts. All right, so here's your homework answers. Where is it? Okay, so here's your homework answers. If you want to take a second or two and check, make sure that you check. So you had your first test this last week. Did anybody have trouble getting into the test or anything like that? We're all good? So I will, if I didn't already grade it, because I think I graded some, I think it was Sunday. I graded some. You guys got about 15 minutes, so you're good. But if I already graded yours, you're good. If I didn't already grade it, it'll get done today. So if you're already done, here's what I'd like you to do. You've done this, and I'll put up the next one too. I'll put them back and forth. Here's what I'd like you to do. You can help clean up lab by simply disassembling everything. So you take the ring stands apart, you put all of the ring stands, like all of the shafts in one pile, the bases in one pile, just put everything into piles, and those can go, the stands, the test tube racks, they can go over in the wash bin as one piece. You don't have to take them apart. But if you take stuff apart for me, it saves me lots of time. Outstanding, people. You are good, smart people. Are they used?
Yeah.
Then go in the trash. Thank you, honey. I'm starving, people. And you can take the clamps off you know, there's a separate test tube clamp on the clamp. You can unscrew those too if you want. Thank you.
You want the spatulas and the glass side?
Yeah, they can all get washed.
Yeah. I understand, but
But now,
it's a.
has anyone got any,
Yeah, the beer's all here.
no, the.
Yeah, you only take one.
I found several good Emily DeChatelet videos, and some of them were like really kid-geared and goofy, and the others were like not appropriate. Really were not, I was like, wait a minute. My only family grew up on YouTube, it's like,
Either small children or.
yeah, not like crazy adult, not like you could watch it, but I'm not showing you the class, you know what I mean?
And put at the bottom, you need to give us the point. Like if you had some sort of rent or something. Make it video. Oh, yeah. It's nice.
You guys see that, Gwinnett County Public Schools has the first confirmed case of monkeypox? Everybody, I don't know what? Yeah. They had their first confirmed case of monkeypox. You can leave the two polls together if it helps.
Oh,
Well, what if I've already taken the.
That's okay, that's right, we're taking them apart, it's all right, but you can leave them together if you want. They're hard to get out sometimes. Yeah, because once you take the little, that other piece off, it's not just, I don't know, it gets tricky. If you can't get it, I'm not gonna give them the tool later.
I knew that was Alex's. I knew it.
Oh.
This back foot.
Through Tom's. And more points than that.
Excellent.
I knew that was Alex's. I just knew that.
How'd you know? Are you psychic? I mean, there's no way you could have known.
Just take it.
This kid, man. All right, what did Jack say? Anything
No, that's
else?
mine. It dropped from my check.
Came in on 5 Lauren. My grandma had one of my aunts at 42. Yep. Asking Henry if you don't get divorces. Very good. All right. Oh, yes, and it's a lovely combination. All
Tom.
righty, Jack, we're gonna split. See you later.
Alex, you can go home.
Jack said Sour Patch Kids and toothpaste is not a good experience. Take his
French fries and
advice.
Frosty, yeah.